All right, first thing we're going to talk about today is a little bit weird, okay? I don't know if you even talked about this in Algebra 2. Some Algebra 2 classes would talk about it, some would not. So I'm not really sure where you are on it, but even if you had talked about it, I'm just going to treat this as if you had not seen it before, okay? It's called continuity. Anybody heard that word in math before? Continuity. So let's put a graph on there. Like, if you just said the word continuity, what would you, I mean, does anybody have like a...
To continue?
Okay, continue, right? The word continuity has continuous in it. To continue, it absolutely has to do with that. I'm thinking like, I don't know, like in English class when you're writing or reading a story or reading a novel or something like that, the story has to have continuity and not jump around from here to here, right? There has to be like a main kind of overriding theme, involved and all that kind of stuff. When you think of continuity, okay, stuff that goes together, that just it's kind of seamless. That doesn't just jump, right, from one place to another. Do you hear that part of it? All right, so I'm going to try to relate that to math. Now there are some equations. I'm not even going to really talk about, I don't think they do in here. Yeah, they don't talk about what these equations actually are. They're just going to graph some things, and they're going to give you some weird looking graphs, some graphs you've probably never seen before, but you just have to talk about the continuity of the graph. So for instance, what if I did this? What if I said, yeah, we'll just do this, and watch, we're going to put a little circle right there, and then we're going to continue this. Just try to... So it's a straight line. So pretend it's a straight line. Okay, so there we go. We've got a straight line, but you got this gap in here. This gap means at this particular point, there's no y point associated with it. All right, so you're going along nice and fine. For every single x, there's a y that's associated. Would you agree? Because any point on line has an ordered pair, doesn't it? It's got an x and it's got a y. Any point here has an x and it's got a y. This point right here has an x and a y. Any point here, it's got an x and a y. You follow me? But what does this have? This is open. It doesn't exist. All right? So the line actually doesn't go through this. It's like you're walking along and you jump over a hole, right? The hole is not part of your sidewalk. Sidewalk's not there. You got a big old hole. You follow me? So you're walking around here and you jump over it. So what do you think? Do you think that's continuous, or do you think it's not continuous? Yeah, it's not continuous because it doesn't keep on going nice and smooth without any gaps. You definitely have a gap here, and that's exactly what that is. This is a big old gap. Actually, it's not a big gap. It's just a gap at one particular number. All right. So it's just a gap at one number. So, for instance, if I went 1, 2, 3, 4, let's say that was 4 right here. So if I asked you, is this continuous or discontinuous, is the word we use. Okay, so continuous, let's write these words down. Continuous, or we call it discontinuous. Spell that right, Tiff? Discontinuous, yep. U-O-U-S? Yeah, I guess that's right, isn't it? Okay. Sometimes when I write things, pretty sure it's right, but then it looks weird. You ever do that? Even common words, it looks weird, and I'm like, did I really spell that right? And you're like, yeah. Because vacuum, to use, yeah, that is kind of a weird thing. Anyway, so continuous and discontinuous. So this is a discontinuous function, all right? They call it a discontinuous function. So what I want to find out where it's discontinuous. At what point do you have that gap? All right, so if I say, at what point is it discontinuous, where is the gap? Well, if I come over here to the x, at where? X equals what? 4, all right? That's where it's discontinuous. So if I go over to 4 and I jump up to where that line should be, there's a gap right there, isn't there? Okay, so I would say it's discontinuous at x equals 4. And that's what they're going to ask. So they're going to ask you a couple questions. They're going to say, is the graph continuous or discontinuous, and at what point? Actually, it says, determine the interval of the domain over which each function is discontinuous. Actually, they say continuous. So it's discontinuous right there. All right? So it's discontinuous. Now they said they're talking about the domain, so I'm not caring about the y. I'm just running around, running on this x-axis right here. Okay, I'm just going back and forth on this x-axis, and it's saying, okay, where on this x-axis are you going to have a gap? And you're going to have a gap right here, right? Because if I go up, I'll never touch that graph, will I? So if I'm running up, across left and right on this x-axis, you follow me? So right, put my pen here, and I'm running across this way, running across this way. At every single point on the x-axis, I would be able to touch the y. I'd have a y value associated with it. I'd be able to touch that graph. Except for where? Except for 4, and then if I jump up, it'll never touch that graph, will it? Some people say, yeah, well, it'll touch that circle. Well, the circle indicates that it's nothing there. Okay, it's like it just stops, and then it starts again a little bit after it. Okay, so that's what it means. So it's discontinuous here. The question they're going to ask you is where, over which intervals. I'll just say where. Okay, but the official wording of this, let me read it again. It says determine the intervals of the domain where this function is continuous. So we want to find out, where is it continuous? Where does it keep on going before it has a little break in it? Again, we're running along the x-axis. So where is it continuous? All right, well, how far can we go on the x-axis to the left? We can go all the way where? To negative infinity, exactly. All right, even at negative infinity, you'd be able to jump down here, wouldn't you? Okay, because this keeps on going, doesn't it? Forever and ever and ever. So even at negative infinity, you'd be able to hit this line right here. Agreed? So where does it change? All the way until you get to where? All the way until you get to 4, right? So I'm going to put a comma here. Let me just make sure I'm writing it the way they're writing it. I'm pretty sure I am. Yes, I am. Okay. So it's from negative infinity all the way to 4. Now, do we include 4? No, because 4, right above 4, it's a gap there at 4. Okay. Now, just below 4, there's no gap. The line goes right up until you get to the number 4. So 3.999999999, it's included. But what's the only thing that's not included? 4. Make sense? All right, and then 4.000000001 is included on my graph. It's just 4, right? Not a little bit less, not a little bit more. It's only 4 that's not included. So what do? I go from negative infinity to 4. And you say, well, why do I put 4? Well, if I put this, what does that parentheses mean? Means it's open at 4, which means it does not include 4, right? It means it gets as close as you could possibly get to 4 without actually hitting 4. You get it? So again, I'm running along the x-axis. So I'm here. So I can go as far as I want to the left. Where is that? It's negative infinity. But watch, as I keep on going, every single point is included here, right? Because anywhere on this x-axis, I can drop down and hit the graph until you get to 4. When you get to 4, there's a gap there. So that's what I did. I say you can get really, really close to 4, but you can't include 4. Now, is that the only part where it's continuous? Is it continuous somewhere else? Yeah, from where? From 4 to infinity, right. From 4 to infinity. But again, we cannot include 4, so don't put a bracket there. You put an open parentheses there. So you could go from 4, watch, and if I'm running this way, again, talking about the domain, okay, I want to find where is it continuous along the domain. So if I'm running this way, it starts just a little bit after 4, right? It just doesn't include 4. It's as close as you could possibly get right after 4. And then watch, if I go this way, every single point after 4, I could actually hit that graph, couldn't I? Right? And then that goes all the way to infinity. What do we put in between here? A union, right? And so that's what the domain is, or that's where it's continuous along this domain. What if the gap wasn't there? What if it was just nice and straight all the way through? What would your domain be? From negative infinity to positive infinity, right? Okay, that 4 wouldn't even make a difference, would it, if it kept on going through? But for some reason, there's a little jump right there. Okay, we're not going to talk about why there would be a jump there, why there would be a gap, but there are situations where it can't equal things. Well, for instance, I'll just give you one little example. What if you had like, I don't know, if you wanted to graph this, 3 over x minus 2. Okay, first of all, this would never equal 0, would it? Okay, but you could put a 0 in for x, couldn't you? All right. But what number could you not have? You could put any number in for x that you wanted to, except for what? Come on, we've talked about this. You could put any number that you wanted in for x, except for 2, right? You can't have a 2 in there. So guess what your graph's, now your graph's going to look a little weird because it's an inverse function. It's not going to look like a nice straight line. But guess what there's going to be? There's going to be a little gap, isn't there? If I was to graph it, okay, I can't put, if I had if I was here at 2, there's nowhere on this graph where I could actually put a y value for it, right? Because 2 does not exist, right? If I put a 2 in for there, it would make this thing not exist. It's kind of like this, right? If I put a 4 in there, it makes that not exist. So that's kind of like a little reason why you might have a gap in a graph. All right, it's kind of weird. I told you it was a little bit weird, didn't I? I warned you. Let's do another one. That's kind of easy because you have a nice straight line. Actually, to tell you the truth, these other ones aren't really even that much more difficult. Graphs are real weird looking, and they're graphs that you've probably never seen before. Let's do one like this. I'm just getting this straight from the book. All right, what if you had a circle right here? Actually, let's do that in a different color. Let's go red again. We'll stay with the same color theme here. And what if I had my graph? Oops, wait a minute. It's cold. What if you had one like this, and then watch this. This is circled in, and this goes like that. It's a weird looking graph. We won't worry about how we got that graph. You're not going to have to graph that on your own. Don't worry about that, okay? So all they're going to do is they're going to give you a picture, and they're going to say, actually, hold on a second. Let me look at this. All right, let me give you a little hint here. If you're drawing this graph, like before, I should have said this before because they say this in the book. And it's a good way to say this. I kind of like how they're talking about this. Watch. If I was drawing this line, how do you know if it's continuous or discontinuous? Well, you can look to see if there's a gap in it. But watch this. If I was going to draw this thing, and if I can draw the line without ever having to pick my pencil up or my pen up, okay, you can consider it to be continuous. If at some point you actually have to pick, watch this, if I drew here, 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 what would I have to do? I'd have to actually pick it up, wouldn't I? Start again and draw it again. Make sense? Because look, see, that's one line right there, right? And then that's a separate line right there. Agreed? All right, so I'd actually have to pick it up in order to go again. So if you have to pick your pencil up to keep drawing this function, then it's discontinuous. If I can draw the function nice and smooth without ever having to pick my pen up or my pencil up, then it's continuous. Let's take a look at this one right here. So if I was going to draw this, where would I start? I'd start from the left, wouldn't I? And I would draw all the way to here. But then I got to hop up to that other point. So what would I have to do? I'd have to pick my pen up, wouldn't I? And then come back up here and then start again. So is this continuous or is it discontinuous? It's discontinuous because I actually have to pick it up. Now, all the x's actually are being satisfied. So, I mean, this is x equals 2. This is considered one graph, even though it's two separate parts. It's considered one graph. The 2's not included on this part of it, but it isn't included on this part. But how did you get up to this? You actually had to pick your pencil up to start that graph over again up here, didn't you? So we would call this a what? A discontinuous function. All right. So where is it continuous? We know it's discontinuous at x equals 2. Where is it continuous? From negative infinity to where? To 2, right? And then from where? From 2 to infinity. Does that make sense? All right. So that's the kind of stuff they're going to ask you. They're going to give you a graph, and it's really not that hard. You don't have to know how to graph it, which is really nice because that looks pretty crazy, doesn't it? All right. Like how in the world would you ever graph something like that? Here's another type of graph. Let me show you this one. And this is one that that we will see. All right. Watch what I'm going to do. I'm going to put a dotted line. It's supposed to be vertical. Okay, I'm just trying to draw this by hand here. All right. So pretend it's vertical and it's a dotted line. And then you have a graph. Let's do this in different colors so that it stands out a little bit. There are functions that look like this. Watch, this starts approaching that dotted line, and it gets really, really close to it, but it never actually touches or goes through that dotted line. All right? And this might just keep on going like that. And then you might have another one that does this. Like maybe it starts here, and it gets really, really close again to that dotted line. It gets closer and closer and closer, but it never actually hits. So look at the yellow right here. That's my graph. Where is it continuous? Well, it's got two parts of it, doesn't it? First of all, is it continuous or discontinuous? It's discontinuous, because if I was to graph this yellow, if I'm graphing right here, I could start all the way here, right, and graph like this, never pick up my pen. But in order to get that other part of it, I'd have to pick up my pen, jump over this dotted line, and then start again. So it's discontinuous. Where is it discontinuous? We'll call this 2. There's 1, there's 2. So where is it discontinuous? Where on the x-axis will it never hit the yellow line? At 2, at x equals 2. So it's discontinuous at x equals 2. So where is it continuous? Well, from negative infinity to 2, and from 2 to infinity, and it's open at 2, right? Does not include 2. Now in that other one, this one right here, you'd probably say this. You'd probably say this goes from negative infinity to 2, and it's open there. But look at this part of it. What would I say with this? Would I put open and then a 2? No, because what? It actually includes 2 on this part of the graph, doesn't it? So I would put a bracket right here at 2 and then go to infinity. Everybody see that? I should have thought of that before I did that. All right. It just occurred to me when I saw this other one. So you would put a bracket here on the second part of it. Still discontinuous though, because you had to pick your pencil up. Same thing here. It's still discontinuous, but it's discontinuous at 2. This would go negative infinity to 2, parentheses on both ends, and this would go from 2 to infinity, parentheses on both ends. All right? There's all kinds of weird-looking things like that. Let's just do this one. We'll stick with the yellow. What if we did this? We'll be graphing these in the next few days. Let's make this a different color. Alright. What if we had that? Is that continuous or discontinuous? Yeah, it's continuous, isn't it? Because I could draw this whole thing, right, without ever having to pick my pencil up. There's no gaps in it at all. So I would just say it's continuous. So where is it continuous? Along the domain. Where is it continuous? From where to where? From negative infinity all the way to positive infinity. Okay? So that's not bad, is it? Again, today you don't have to draw those crazy things. Tomorrow we're going to learn how to draw some of those. Not all the crazy ones, but we're going to learn how to draw some of them. So really, the first half of what we're doing today is just getting straight what continuous is and discontinuous. It's really not that big of a deal. Even though the graphs look real weird and ugly, it's real simple. There's really no math involved to do this. You just have to be able to look at the domain and find out where is it continuous. And that's all you have to do for those kind of problems. Pretty simple. Now what they're going to ask you to do is this. They're just going to ask you to graph a straight line. Today, I thought I didn't want to cram it all into today, so I thought I would just do graphing a straight line today, and then tomorrow we're going to graph some stuff that looks like this. Do you remember doing that in Algebra 2?
Parabola.
Yeah, it's a parabola. Very good. Okay, and we're going to graph stuff that looks like this. That might scare you off a little bit, right? It's not as bad as it looks. It looks really ugly and looks crazy. You'd never be able to do it. Yeah, but it's not really that difficult once I give you some techniques, okay? And that's what we're going to work on tomorrow, some techniques. Today we're just going to graph a straight line. So let's see if I have any examples. Well, let's just start off really easy. Watch. What if I said this? What if I said y equals 2x minus 3? And I asked you to graph this thing. Okay? What do we know? We've already talked about this quite a bit, haven't we? There's two things in here. There's this, which is what? What's that negative 3? It's the y-intercept. Good. And then, what's the second thing we need to know? That thing right there, which is the slope. All right, so this shouldn't be that big of a deal. If it's already in slope-intercept form, y equals mx plus b, it's pretty easy to graph. So let's graph it. Negative 3. That's where I start. Okay, I start at the y-intercept. I don't start with a slope. I start with a y-intercept. So I come down here on the y-axis. Remember, this is the x-axis. This is the y-axis. 1, 2, 3. So it's where it crosses the y-axis. So I'd put a dot at negative 3. Make sure everybody can do this, okay? Everybody in here should be able to do this. If I give it to you in slope-intercept form, everybody should be able to graph it. It's not difficult at all. Just put the y-intercept right here. That's where it's going to cross the y-axis. But now we got to figure out what the slope's going to be, what the slant of this line is. So you look over here. It's 2, isn't it? Now, slope is rise over run, isn't it? So sometimes it's nice to put a denominator there. Because when it's a whole number, some people forget to do the run part of it. So this means rise over run, 2 over 1. So what do? We rise 2 from this y-intercept, okay? Don't start at the origin. Start at the y-intercept and rise 2. 1, 2. And then we run 1. Means we go to the right 1 place. We put a dot right there. That's all it is. Put 2 dots. But then what do you do after you get the 2 dots? Just connect them. Right, exactly. Connect them. And it's going to look like that. Technically, keeps on going, so you put arrows. If you don't put the arrows, I don't really care. But that's what it would look like. Don't just connect between one dot and the other dot. Make sure it keeps on going a little bit. Take up your whole graph. All right? And that's exactly what you do. Now, the worksheet I'm going to give you today, it's not quite as easy as this because I don't give you these equations in slope-intercept form. What you're going to have to do is you're going to have to solve for y and put it in slope-intercept form. All right? So let me make one up. I don't know if it's going to come out real pretty or not. I kind of doubt it will. So they don't really give you too many of these in the book. But on the worksheet, there's quite a few of them. So let me just make it up. All right, watch. What if I had 3x plus 2y equals 8? All right? There you go. And if I asked you to graph this, would you be able to graph something like this? Don't graph it the way it looks right now. All right? Change it first, okay? So don't even start graphing yet. Change it first in the slope-intercept form. So I'll give you a second to do that. You want this y equals mx plus b. So go ahead and do that. All right, that should be enough time. Let's get y by itself. First thing we do is subtract a 3x. Watch how easy this is. This shouldn't take long at all. So we subtract a 3x. You don't have to show that it's subtracted from this side. You know it's going to go away, right, when you subtract it. So let's just try to streamline this as best as we can. So if I subtract a 3x here, I subtract a 3x here, I always put that out in front of the 8, in front of the whole number, because I want it y equals mx plus b, so the x goes first. And then we divide by 2. We've been doing this to find the slopes. Remember the perpendicular parallel problems? Remember we had to do that? Find the equation of a line is perpendicular to this, parallel to this. So we've done this before. So divide that by 2, divide that by 2. So look what we get. We get y equals negative 3 over 2x plus what? 4. I did rig this a little bit so the y-intercept comes out to a nice whole number. All right, wasn't that hard. So now what do? We graph this thing. So the y-intercept is 4. So 1, 2, 3, 4. And then we put a dot right here. So we always start with the y-intercept. Make sure you include the sign. If it's positive, it goes up. If it's negative, it goes down. So we put a dot at positive 4. Now what do you look for? The slope. The slope is negative 3 over 2. Now look, you could, remember it's rise over run. You could rise negative 3 and run positive 2. Or you could do what else? You could rise what? Positive 3 and run what? Negative 2. Okay? I'll do it both ways just to show you. So let's do the first one, negative 3 over 2. So we start right here. We rise negative 3, which means we go down 3. 1, 2, 3. And we run positive 2, which means we go to the right 2 places. We put a dot right there. You could just stop right there, connect the points, and you're done. I just want to show you that you could go the other way. You could rise 3 and run negative 2. Watch. 1, 2, 3. 1, 2. Look at that. Still lies on the same line, doesn't it? All right, so it doesn't matter which way you go if you have a negative. So let's connect them. It's pretty good. Again, I don't want to start and stop at my endpoints there. It just looks a little nicer if you extend it out a little bit. And there you go. Look, both of those points lie on this line right here, don't they? So I could rise, I could go up and to the left, or I can go down and to the right. I'm still going to be at the same line, and there's my graph. That's all there is to it. We good with that? All right. That's all I got. You're going to have several of these to do. Let's see, 1, 2, 3, 4 of these. There's only 6 problems on this whole worksheet. This is really simple, okay? We got 10 minutes left, so you probably have time to finish all of these in these next 10 minutes. So I'll give this to you. This is section 3.5a is the worksheet, okay? So worksheet 3.5a.